Hello, friend. Welcome back. Or maybe this is your first time here. Either way, I'm glad you found this quiet corner of the universe. Some nights when the sky feels impossibly vast and the stars breathe slower than they should, you might wonder what else is out there. Not just other worlds, but other kinds of worlds. Places so strange they make Earth seem like the only normal thing in an abnormal cosmos. Tonight, we're going to drift through the strangest planets ever discovered, worlds where glass rains sideways through hurricane winds, where one side burns in eternal daylight, while the other freezes in endless dark, where oceans aren't made of water, but of molten rock that glows like dying embers. Before we begin our journey together, if you find comfort in these quiet explorations of the cosmos, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories, told softly, and ring the little bell, not for noise, but so the next quiet night can find you again. Thank you for being here. Now, let's drift. The universe is older than we can properly imagine. 13.8 billion years of stars being born, living, and dying. 13.8 billion years of planets forming in the aftermath, swirling together from dust and violence and time. Scientists estimate there might be more planets in our galaxy than there are grains of sand on all of Earth's beaches. Some calculations suggest 20 billion Earth-sized worlds in the Milky Way alone, just in what astronomers call the habitable zone. That delicate distance from a star where water could exist as liquid. But habitable doesn't mean familiar. It doesn't even mean comfortable. When Galileo first turned his telescope toward Jupiter in 1610, he saw 4 small points of light dancing around the giant planet. Moons, worlds circling another world. It was a quiet revolution, proof that not everything orbits Earth, that the cosmos is stranger and more diverse than anyone had imagined. But Galileo had no idea. Those 4 Galilean moons, Io, Europa, Ganymede, Callisto, they were just the beginning of strangeness. Today we found planets that would have broken his telescope and his mind. We found worlds that rewrite what we thought a planet could be. But what makes a planet weird? It's a fair question. Scientists suggest it's not just about being different from Earth, though that's part of it. It's about defying what we thought were the rules. When the first exoplanet orbiting a sun-like star was confirmed in 1995, a world called 51 Pegasi, B astronomers were stunned. This planet, roughly half the mass of Jupiter, orbited its star in just over 4 days. 4 days. Mercury, the fastest planet in our solar system, takes 88 days to circle the sun. This new world was so close to its star that its surface temperature was estimated at around 1,000 degrees Celsius. Hot Jupiters, they called them. Gas giants hugging their stars in impossibly tight orbits. It was the first sign that our solar system, with its orderly rocky planets near the sun and gas giants farther out, might be the exception, not the rule. The universe, it seems, doesn't follow our expectations. It creates and destroys according to physics, not according to what seems reasonable to human minds. Since that discovery, we've found more than 5,000 confirmed exoplanets. Each one is a data point in the great catalog of cosmic possibility. Some are unremarkable, quietly orbiting unremarkable stars. But others, the ones we're here to talk about tonight, are the outliers, the strange jewels in the darkness. Research shows that the definition of weird keeps changing. 20 years ago, a planet twice Earth's mass would have been fascinating. Now we found planets 30 times more massive planets, smaller than Mercury planets, that shouldn't exist according to our models, but do anyway. The universe doesn't care about our models. It just keeps making things. You might wonder how we even find these distant worlds. Most are invisible too far and too dim to see directly even with our best telescopes. Instead, astronomers use clever tricks. The transit method watches for tiny dips in a star's brightness when a planet passes in front of it, like a moth crossing a distant streetlight. The radial velocity method detects the subtle wobble a planet's gravity causes in its parent star, the way a child on a swing pulls slightly on the chains. Gravitational microlensing watches for the bending of light when a massive object passes between us and a more distant star, briefly magnifying the background light like a cosmic magnifying glass. Each method has its strengths. Each reveals different kinds of strangeness. Together, they've painted a picture of a galaxy far more diverse and unexpected than we ever dreamed. Some of these worlds challenge our understanding of planetary formation. Scientists believe planets form from protoplanetary disks, vast spinning clouds of gas and dust around young stars. Over millions of years, particles stick together, growing from pebbles to boulders to mountains to worlds. Rocky planets form close to the star, where it's hot enough that only rock and metal can condense. Gas giants form farther out, where ice and gas can accumulate. That's the theory. That's what happened here in our orderly little solar system. But the universe is full of planetary systems that don't follow the script. Hot Jupiters near their stars, super-Earths that have no equivalent in our neighborhood. Ice giants in places too warm for ice. It seems as though planetary migration is common worlds drifting inward or outward from where they formed, pushed by gravitational interactions with other planets or with the remnants of the protoplanetary disk itself. What we're learning is that planet formation is chaotic, violent, full of collisions and ejections and lucky accidents. Earth itself is thought to have been hit by a Mars-sized object called Theia about 4.5 billion years ago. That catastrophic impact threw debris into orbit that eventually coalesced into our moon. We are, in a sense, the children of cosmic violence. So is everything else out there. But tonight we're not here to talk about the ordinary chaos. We're here for the truly strange. The planets that make astronomers stop and recalculate, that force us to expand our definitions, that remind us the universe will always be stranger than we expect. Here's something to consider. When we call a planet weird, we're really saying it's different from what we know. But from the perspective of a being on that world, if such a being could exist, their planet would be normal. It's only weird to us because we're standing on Earth, a temperate world with liquid water and a breathable atmosphere orbiting a stable yellow star at exactly the right distance. We won the cosmic lottery. We're the outliers. Most planets are not like Earth. Most are hostile, extreme, unlivable. Perhaps the real weirdness is expecting anything else. The Kepler Space Telescope, launched in 2009, was designed to stare at a single patch of sky containing about 150,000 stars. It watched them continuously looking for the telltale dimming that signals a planet crossing in front of its star. Over its 9-year mission, it discovered more than 2,700 confirmed exoplanets and thousands more candidates still being verified. Each discovery added a new thread to the tapestry of cosmic diversity. Some scientists joke that Kepler taught us there are more ways to be a planet than we ever imagined. Rocky planets, yes. Gas giants, certainly. But also mini-Neptunes, super-Earths, sub-Neptunes, planets in binary star systems. Planets around dead stars, called pulsars, planets with no star at all. It seems as though the universe is less interested in following rules and more interested in trying everything at least once. Gravity and chemistry and time, given enough space and enough chances, will create every possible variation. We're just beginning to catalog them all. One of the strangest lessons from exoplanet research is about our own expectations. For decades, scientists assumed that life, if it existed elsewhere, would need an Earth-like planet. Liquid water, moderate temperatures, a stable star. But the more we learn about extremophiles on Earth, organisms that thrive in boiling acid springs and Antarctic ice, in the crushing depths of ocean trenches, the more we realize life might be more adaptable than we thought. Maybe weird planets aren't obstacles to life. Maybe they're just different kinds of opportunities. Maybe somewhere out there something lives on a world we would consider impossible. Maybe strangeness is only strange until you understand it. But understanding takes time, and tonight we have time. We have 105 minutes to drift through the cosmos, to visit worlds that challenge everything we thought we knew about planets. We'll see storms that would shred our strongest materials. We'll stand on boundaries between eternal light and eternal darkness. We'll float through oceans deeper than any on Earth and hotter than any forge. You don't need to understand everything. That's not the point. The point is to feel the vastness, to remember that we're small and the universe is large and full of wonders we're only beginning to glimpse. The point is to rest in that feeling, to let curiosity do the listening while your mind drifts through the dark. So, take a breath. Let the world slow down. Let the stars breathe a little slower. We're going to start with the planets where the weather itself becomes art, where the sky doesn't just rain water, but rains materials that would seem impossible, beautiful, deadly. We're going to talk about glass and diamonds and iron falling from alien skies. Imagine standing beneath a sky where the rain doesn't fall down, but flies sideways at 7,000 kilometers per hour. Each droplet a shard of molten glass that could slice through steel. Imagine clouds made of vaporized rock winds that scream louder than any hurricane Earth has ever known, and storms that have raged for longer than human civilization has existed. This isn't science fiction. This is weather on worlds we've actually found drifting in the darkness beyond our solar system. On Earth, we complain about rain. We carry umbrellas, we check forecasts, we cancel picnics. But Earth's weather, even at its most violent, is gentle compared to what happens on some exoplanets. Our hurricanes, our tornadoes, our blizzards. They're whispers compared to the screaming chaos on worlds like HD 189-733b. HD 189-733b orbits a star about 63 light-years from Earth in the constellation Vulpecula. It was discovered in 2005 using the transit method watching as it passed in front of its parent star and dimmed the light by a measurable amount. At first glance, it seemed like another hot Jupiter, a gas giant orbiting very close to its star. Scientists calculated its orbital period at just 2.2 days. Its surface temperature, they estimated, reaches about 1,000 degrees Celsius on the day side. But then researchers used the Hubble Space Telescope to analyze the planet's atmosphere, breaking down the light that filtered through it during transits. What they found was unexpected. The atmosphere contains silicate particles, tiny fragments of silicon and oxygen, the same materials that make up glass here on Earth. Research shows these particles exist in the upper atmosphere, where temperatures are high enough to vaporize rock. As the particles condense, they form clouds, but not water clouds. Glass clouds. Now, here's where it gets strange. HD 189-733b rotates, but it's also tidally locked to its star, meaning one side permanently faces the heat, while the other faces away into relative cold. But the planet's atmosphere doesn't stay still. The temperature difference between the day side and night side creates winds powerful atmospheric currents that race around the planet. Scientists suggest these winds reach speeds of about 7,000 kilometers per hour, nearly 20 times faster than the speed of sound on Earth. When those winds hit the glass clouds, they tear them apart. The silicate particles, superheated and sharp, are flung horizontally across the planet. It rains glass, but the rain doesn't fall. It flies sideways through the scorching atmosphere like a billion tiny knives. If you could somehow stand on this world, which you couldn't because there's no solid surface and the heat would vaporize you instantly, you would be shredded by glass moving faster than any bullet. It's beautiful in a terrible way. Deadly beauty. The kind of thing that exists in the universe not because it's meant for anything, but simply because physics allows it. The same forces that create gentle rain on Earth create glass hurricanes on HD 189-733b. Same principles, different conditions, completely different outcome. Astronomers actually observed this planet's color using spectroscopy. It appears deep blue, almost like Earth when viewed from space. But it's not blue from oceans. It's blue because the silicate particles in the atmosphere, scatter blue light the same way our sky is blue because of Rayleigh's scattering in our atmosphere. From a distance, HD 189733b might look inviting, familiar even. A blue marble in the black. Up close, it's hell rendered in azure. Now let's travel to another world, one where the very ground beneath your feet might be made of compressed carbon. 55 Cancri E orbits a star about 41 light-years away in the constellation Cancer. This planet was discovered in 2004, but it took years of additional observations to understand just how strange it really is. It's classified as a super-Earth, about twice the radius of our planet and roughly 8 times more massive. It orbits incredibly close to its star, completing one orbit every 18 hours. 18 hours. Earth takes 365 days. Because of this proximity, the surface temperature on 55 Cancri E reaches about 2,400 degrees Celsius on the day side, hot enough to melt most metals. Scientists initially thought it might be a rocky planet, similar to Earth, but larger and much hotter. But when researchers analyzed its mass and radius more carefully, something didn't add up. The density was wrong. It was too dense to be just rock and iron. Research published in 2012 suggested something extraordinary. Based on the planet's density and its parent star's composition, which is rich in carbon relative to oxygen, scientists believe 55 Cancri E might have a carbon-rich interior. In high-pressure, high-temperature environments, carbon doesn't stay as graphite. It crystallizes into diamond. The models suggest that as much as a third of this planet's mass could be diamond, a layer of crystallized carbon kilometers, thick beneath a surface of graphite and silicon carbide. A diamond planet. It sounds like fantasy, like something from a fairy tale told to children who dream of treasure. But the chemistry is sound. Carbon under extreme pressure and heat forms diamond naturally. On Earth, diamonds form deep in the mantle and are brought to the surface by volcanic activity. On 55 Cancri E, the entire structure of the planet creates the right conditions for diamond formation on a planetary scale. Of course, you couldn't mine it. You couldn't even land on it. The surface temperature would incinerate any spacecraft, any tool, any human foolish enough to try. And even if you could somehow extract diamonds from this world, they would be worthless. Scarcity creates value, and there's nothing scarce about a planet made of diamond. It would be like bringing back seawater from another world. Impressive perhaps, but not valuable. It seems as though the universe has a sense of irony. The most precious materials on Earth, the things we fight over and treasure and lock in vaults, might be as common as rock on other worlds. Value is relative. Rarity is contextual. What we cherish here might be garbage elsewhere. But 55 Cancri E holds another mystery. Observations from the Spitzer Space Telescope detected variations in the infrared light coming from the planet, suggesting its surface temperature changes dramatically over time. Scientists weren't sure why at first. Tidal locking should create a stable temperature pattern, hot on one side, cooler on the other. But the data showed fluctuations sometimes by hundreds of degrees on timescales of hours to days. One hypothesis suggests the planet might have volcanic activity, massive eruptions that temporarily change the surface temperature and atmospheric composition. Another idea proposes that the planet's atmosphere might be dynamic, with clouds of vaporized rock forming and dissipating, creating temporary cooling effects. A third possibility is that the planet's orbit might be slightly eccentric, bringing it closer and farther from its star in a pattern that creates thermal variations. We don't know yet, and that's part of the wonder, isn't it? Even with all our telescopes and all our data, these distant worlds still keep secrets. They reveal themselves slowly, layer by layer, mystery by mystery. Let's visit one more world where the weather defies imagination. WASP-76b, discovered in 2016, orbits a star about 640 light-years from Earth. It's another hot Jupiter, but with a twist that makes it stand out even among the strange catalog of exoplanets. This world is tidally locked, like the others we've discussed, with a permanent dayside and permanent nightside. The dayside temperature reaches about 2,400 degrees Celsius. The nightside is cooler, around 1,500 degrees Celsius, still far hotter than any oven on Earth, but relatively cool for this planet. Scientists using the espresso spectrograph on the Very Large Telescope in Chile analyzed the light from WASP-76b's atmosphere in remarkable detail. What they found was iron vapor. On the scorching dayside, temperatures are high enough to vaporize metals. Iron, which melts at about 1,500 degrees Celsius and boils at nearly 3,000 degrees, exists as a gas in the atmosphere. The powerful winds generated by the temperature difference between day and night carry this iron vapor across the planet toward the cooler night side. But here's where it gets fascinating. As the iron vapor crosses into the night side, it cools. And when iron vapor cools below its condensation point, it turns back into liquid. It condenses into droplets. Research shows that on the night side of WASP-76b, it rains iron, molten iron droplets falling from clouds of metal vapor, splashing onto whatever surface exists below, if there is a surface at all beneath the thick atmosphere. Think about that for a moment. Rain made of liquid metal, each drop glowing orange-red with heat, falling through an atmosphere thick with vaporized minerals and extreme pressure. It's the kind of image that seems impossible until you remember that the universe doesn't care what seems possible to us. It just follows physics wherever physics leads. Scientists detected this iron rain using a technique called spectroscopy, which analyzes how light is absorbed and emitted at different wavelengths. When light from the star passes through WASP-76b's atmosphere during a transit, certain wavelengths are absorbed by specific elements. Iron has a distinctive spectral signature. Researchers found strong iron absorption on the evening side of the planet, where the day transitions to night, exactly where you'd expect iron vapor to condense if the hypothesis about iron rain is correct. It's indirect evidence, but it's compelling. We can't see the rain directly. We can't send a probe to stand beneath those metal clouds. But we can read the story written in the light, decode the messages carried across 640 light-years of space, and reconstruct what must be happening on that distant, violent world. Have you ever wondered what it would sound like? Iron rain hitting a surface. Earth's rain has a rhythm, a percussion that varies with the size of the drops and what they're falling on. Gentle rain on leaves sounds different from heavy rain on pavement. But iron drops would be denser, heavier, hotter. Would they hiss and steam? Would they thunder? Would they sound like a forge, like a billion tiny hammers working metal? We'll never know. Sound doesn't travel through the vacuum of space, and even if it did, there's no one there to hear it. These three worlds, HD189-733b55, Cancri E, and WASP-76b, they show us that weather isn't just about water and wind. Weather is about energy transfer, about heat moving from one place to another, about materials changing state under pressure and temperature. On Earth, we have a water cycle. Water evaporates from oceans, forms, clouds falls as rain flows back to the oceans. Simple, stable, life-sustaining. On these exoplanets, the same fundamental process creates cycles of glass, of diamond formation, of metal vapor, and liquid iron. Scientists sometimes talk about the anthropic principle, the idea that the universe seems fine-tuned for life because we're here observing it. But discoveries like these remind us that most of the universe isn't fine-tuned for anything. Most of it is chaos and extremes and conditions that would destroy us instantly. We exist in a tiny bubble of habitability on a planet that happens to orbit at just the right distance from a star that happens to be stable enough to allow complex chemistry to develop over billions of years. We're not the rule. We're the exception that got lucky enough to ask questions about the rule. But even in the chaos, even in the glass storms and iron rain, there's a kind of order. Patterns emerge. Physics creates structures, gravity shapes worlds, temperature drives, winds, pressure changes states. The universe might be strange, but it's not random. Everything happens for a reason, even if that reason is just thermodynamics and time. As we drift onward through the catalog of cosmic strangeness, we're going to leave these scorching worlds behind and visit places where the very concept of day and night breaks down, where the sun never rises and never sets, where half the world burns while the other half freezes, and a thin band between them might be the strangest place of all. What would it be like to live in a place where the sun never moves, where dawn never comes, because night never fell, where the sky stays frozen in the same position forever, neither rising nor setting, just hanging there like a painting on the ceiling of the world? No morning light to wake you, no sunset to mark the end of the day. Just endless unchanging light on one side, endless unchanging darkness on the other, and a narrow ribbon between them, where the sun sits permanently on the horizon, painting the sky in eternal twilight colors. This isn't poetry. This is the reality on tidally locked planets' worlds that show the same face to their star, the way the moon shows the same face to Earth. And these worlds might be among the most common in the galaxy, the most likely places we'll search for life beyond our solar system, even though they break almost every assumption we've made about what a habitable world should look like. Tidal locking happens through a process that's surprisingly gentle given enough time. When a planet orbits close to its star, the star's gravity pulls slightly harder on the near side than the far side. This creates a tidal bulge, the same force that creates ocean tides on Earth. But unlike Earth's liquid oceans, a planet's entire body experiences this tidal force. Over millions of years, the friction from this gravitational gradient slows the planet's rotation. Eventually, the planet reaches a state where its rotation period matches its orbital period perfectly. One side faces the star always. The other side faces away always. The planet becomes lock-synchronized like a cosmic dance where partners never let go. Our moon is tidally locked to Earth. That's why we always see the same face, why there's a near side and a far side, though not a dark side, since the far side gets plenty of sunlight during the lunar month. Mercury is in a different kind of resonance with the sun, rotating 3 times for every 2 orbits, a more complex but equally stable pattern. But many exoplanets we've discovered are in simple 1-to-1 tidal locks, especially the small rocky planets orbiting red dwarf stars. Red dwarfs are the most common type of star in the galaxy, making up about 70% of all stars. They're small, cool, long-lived, burning their hydrogen fuel so slowly they could shine for trillions of years. But their habitable zones, the regions where liquid water could exist, are very close to the star. For a planet around a red dwarf to receive the same amount of energy Earth gets from the sun, it has to orbit much closer. And at that distance, tidal locking happens relatively quickly in astronomical terms, sometimes in just a few 100 million years. Proxima Centauri b, discovered in 2016, orbits the closest star to our solar system. Proxima Centauri just 4.2 light-years away. This planet is roughly Earth mass, perhaps 1.3 times our planet's mass, and it orbits in the habitable zone. Its orbital period is about 11.2 days. Scientists strongly suspect it's tidally locked, though this hasn't been confirmed directly since we can't resolve the planet's surface from this distance. If Proxima Centauri b is indeed tidally locked, one hemisphere experiences perpetual day under a star that appears much larger in the sky than our sun does from Earth, because the planet orbits so close. The other hemisphere exists in perpetual night, never seeing the star lit only by starlight, and perhaps by auroras if the planet has a magnetic field. Research shows the day side might reach temperatures around 30 degrees Celsius, warm enough for liquid water. The night side could plunge to minus 40 degrees Celsius, or cold enough to freeze carbon dioxide from the atmosphere. Now, imagine living there. Imagine cities built on the day side under a sun that never sets, where clocks measure passing time. but the sky never changes. Or imagine settlements on the night side in eternal darkness, broken only by artificial light, where the concept of a day becomes purely arbitrary, a memory carried from another world. Or imagine the most intriguing possibility cities built along the Terminator, the boundary line between day and night, where the sun sits forever on the horizon. The Terminator zone would be a ribbon circling the entire planet, a region perhaps a few hundred kilometers wide, where the temperature might be moderate, where the sunlight comes in at a perpetual low angle like permanent sunset. Scientists suggest this zone might be the most habitable region on a tidally locked planet, avoiding the extremes of both the scorching day side and frozen night side. It would be a world of permanent twilight, of long shadows and soft light of horizons that glow but never brighten into full day. But living on a tidally locked world would require adapting to a fundamentally different experience of time. On Earth, our biology evolved with the rhythm of day and night. Our circadian rhythms, the internal clocks that regulate sleep and wakefulness, are tuned to a 24-hour cycle. We feel tired at night alert during the day because millions of years of evolution shaped us for a rotating world. On a tidally locked planet, that rhythm would be meaningless. There would be no natural cycle to entrain, to no external cue to tell your body when to rest. Would humans adapt? Would we create artificial cycles, designated sleep periods, and wake periods purely by convention? Would some people prefer the day side and others the night side, a fundamental division based on personal chronotype? Would children born on such a world even develop circadian rhythms? Or would they experience time in a completely different way? We don't know. But it's a reminder that so much of what we consider fundamental about existence is actually contingent on the specific conditions of Earth. The cycle of day and night seems universal until you remember it's just a consequence of rotation. Time itself doesn't have days. We invented days to measure time. On another world, time would still pass, but the markers would be different. The TRAPPIST-1 system discovered in 2017 offers an even more fascinating glimpse into tidally locked worlds. This system contains 7 roughly Earth-sized planets orbiting an ultra-cool red dwarf star about 40 light-years from Earth. The star is only slightly larger than Jupiter, though much more massive. 3 of the 7 planets, TRAPPIST-1, E, F, and G, orbit within the habitable zone. Scientists believe all 7 planets are likely tidally locked because of their proximity to the star. What makes this system extraordinary is that the planets are packed so tightly together that if you stood on one, you could potentially see the others in the sky, not as points of light like we see Venus or Mars, but as distinct disks, perhaps even large enough to show features. Research published in Nature Astronomy suggests the planets are close enough that gravitational interactions between them can be measured, allowing scientists to calculate their masses with remarkable precision. TRAPPIST-1e is considered one of the most potentially habitable exoplanets discovered so far. It's about 92% Earth's diameter, and models suggest it could have liquid water on its surface. But again, if it's tidally locked, that water would be distributed in strange ways. The day side might have a warm ocean. The night side might be covered in ice kilometers thick. Or perhaps atmospheric winds would redistribute heat, creating a more temperate climate across the whole planet. Atmospheric circulation becomes crucial on tidally locked worlds. If the atmosphere is too thin, heat won't transfer efficiently from the day side to the night side. The day side would bake, the night side would freeze, and the habitable zone would be limited to a narrow band around the Terminator. But if the atmosphere is thick and dynamic, with strong winds and efficient heat transport, the temperature difference between hemispheres could be much smaller. Earth's atmosphere redistributes heat from the equator to the poles, making the entire planet more habitable than it would be without weather. On a tidally locked world, the same principle applies, but the gradient is even more extreme, from perpetual heating to perpetual cooling. Computer models simulating tidally locked planets suggest that atmospheric circulation patterns would be dramatically different from Earth's. Instead of the familiar Hadley cells, Ferrous cells, and polar cells that drive our weather, a tidally locked planet might develop a single large circulation pattern with hot air rising on the day side, flowing toward the night side at high altitude, cooling and sinking on the night side, then flowing back toward the day side at low altitude. It's called a substellar to antistellar circulation, and it would create permanent wind patterns unlike anything on Earth. Imagine standing on the day side, feeling a perpetual breeze blowing away from the sun, carrying heat toward the darkness. Imagine standing on the night side, feeling a cold wind always blowing toward the distant glow on the horizon. The weather wouldn't change. It would just be a permanent state, stable and strange. But here's something that challenges our assumptions about tidal locking. Some scientists suggest that even if a planet is tidally locked to its star, it might not be completely static. If the planet has a thick atmosphere, thermal tides, atmospheric bulges caused by heating, could create torques that cause the planet to rock back and forth, slightly a phenomenon called libration. The planet would still show predominantly the same face to its star, but not exactly. There might be a slow wobble causing the sun to move slightly in the sky over long periods, rising and setting over weeks or months instead of hours. It's a small variation, but it would mean the difference between absolute permanence and slow change. Even in the most locked worlds, time might still create subtle rhythms. The universe resists absolute stasis. Everything shifts eventually, even if just a little. One of the common mistakes people make when thinking about tidally locked planets is assuming they're automatically uninhabitable. The logic seems sound at first. Extreme temperature differences one side, too hot, the other, too cold, only a small region in between where life could survive. But research shows this assumption might be wrong. Life on Earth exists in an extraordinary range of environments, from deep-sea hydrothermal vents at 400 degrees Celsius to Antarctic valleys at -90 degrees. Life adapts, life spreads, life finds ways. On a tidally locked planet with oceans, life might begin in the moderate terminator zone and then spread, adapting to hotter regions on the day side or colder regions creeping into the night. Or life might develop independently in different zones, creating separate biospheres adapted to perpetual light or perpetual dark. Or perhaps life would thrive in the oceans, where water's heat capacity would moderate temperature extremes, making the underwater environment more stable than the surface. We project our assumptions onto other worlds, but those assumptions are based on one example: Earth, and Earth rotates. Everything we think we know about habitability is conditioned by that rotation. When we find planets that don't rotate the same way, we have to question everything. What is essential for life? What is just familiar? Tidal locking also creates interesting possibilities for atmospheric chemistry. On Earth, photosynthesis occurs during daylight producing oxygen, while respiration occurs continuously consuming oxygen. The balance between these processes maintains atmospheric oxygen levels. On a tidally locked planet with life, you might have permanent photosynthesis on the day side and permanent respiration everywhere. The atmospheric chemistry could develop gradients with higher oxygen concentrations on the day side and different gas mixtures on the night side. It would be like a planet-sized laboratory running continuous experiments in chemical equilibrium. Scientists are particularly interested in studying the atmospheres of tidally locked planets because they might be easier to characterize than Earth-like planets. When a tidally locked planet transits its star, the starlight passes through different parts of the atmosphere depending on the orientation. By comparing spectra from the day side, night side, and terminator, researchers can build a three-dimensional picture of atmospheric composition and temperature structure. It's like reading the planet's story written in the light. The James Webb Space Telescope, launched in 2021, has the capability to analyze exoplanet atmospheres in unprecedented detail. One of its early targets was TRAPPIST. Though initial observations haven't detected significant atmospheres on some of the planets. This doesn't mean they're airless, just that their atmospheres might be thinner or more transparent than scientists hoped. but the search continues. Each observation teaches us something, even if it's not what we expected. Here's something to consider. If we ever send signal to potentially habitable exoplanets, if we try to communicate with possible civilizations on tidally locked worlds, how would they conceptualize time? Would they understand the message encoded in pulses based on our 24-hour day? Or would their mathematics, their language, their entire framework for understanding the universe be built on different foundations? We think of time as universal, but the way we measure it, the way we experience it, that's entirely local. As we drift further into the cosmic catalog, leaving these half-lit worlds behind, we're going to encounter planets even more isolated, even stranger. Worlds that don't orbit any star at all. Worlds cast out into the darkness, wandering alone through the galaxy, carrying whatever heat they have left, from their formation, slowly cooling across billions of years. Worlds where night is not half the cycle, but the entire existence. Cold, dark, free. Picture a world drifting through the void between stars, a place where the sky holds no sun, where the only light comes from distant galaxies too far away to cast even a shadow. No dawn, no seasons, no orbit. Just endless falling through the dark alone, untethered from any star, carrying nothing but the fading memory of heat from its birth. These planets exist. They're called rogue planets, and there might be billions of them wandering our galaxy, invisible ghosts sailing through the emptiness, and we're only just beginning to understand how strange and how common they truly are. The story of rogue planets begins with a problem. When astronomers started building models of planetary system formation in the 1980s and 90s, they noticed something odd in the simulations. Young planetary systems are chaotic places, multiple planets forming at once gravitationally interacting, their orbits shifting and changing. Sometimes these interactions become violent. A close encounter between two planets can fling one of them outward, accelerating it past escape velocity, sending it tumbling out of the system entirely. The simulations showed this happened regularly. For every stable planetary system that emerges, several planets get ejected into interstellar space. At first, this seemed like a curiosity, a minor detail in the larger story of planet formation. But then researchers started calculating how many planets might have been ejected over the billions of years since the galaxy formed. The numbers were staggering. Some estimates suggest there could be more rogue planets in the Milky Way than there are stars, possibly twice as many, maybe more. Trillions of worlds drifting in the dark, outnumbering the planets that orbit stars, forming a hidden population we barely knew existed. The first challenge was figuring out how to detect them. Planets shine only by reflected light from their stars. A rogue planet has no star, so it's almost completely dark and visible against the black background of space. Even the largest rogue planet would be impossibly dim, colder than the coldest depths of space, radiating only faint infrared heat left over from its formation. Finding one would be like trying to spot a single grain of black sand scattered somewhere across an ocean at night. But astronomers are clever. They realized they could use gravity itself as a detection method. Einstein's general relativity tells us that mass bends space-time, and light follows the curves of space-time. When a massive object passes between us and a more distant star, the object's gravity acts like a lens, bending the starlight around it and briefly magnifying it. This is called gravitational microlensing, and it works even if the lensing object is completely dark. The first confirmed detection of a possible rogue planet using microlensing came from observations collected over years by survey projects like OGL, the Optical Gravitational Lensing Experiment, and MOA microlensing observations in astrophysics. These projects monitor millions of stars, simultaneously watching for the telltale brightening that signals a microlensing event. Most events are caused by stars passing in front of other stars, but some brightenings are too brief and too subtle to be stellar. The duration and shape of the brightness curve reveal the mass of the lensing object. When that mass is planetary, somewhere between Earth-sized and Jupiter-sized, and there's no evidence of a nearby star. It suggests a rogue planet. In 2011, a team of astronomers published results in Nature describing the detection of 10 candidate Jupiter-mass rogue planets. The paper suggested that Jupiter-sized rogues might outnumber main sequence stars by a factor of nearly 2 to 1. That was the first real hint of just how populous this hidden population might be. More recent studies using data from surveys like the Kepler mission's K2 campaign and ground-based observations have refined these estimates, though uncertainty remains large. Research shows that rogue planets likely form in 2 main ways. The first is ejection, the scenario the early simulations predicted. During the chaotic phase of planetary system formation, gravitational interactions between young planets can kick one or more of them out of the system entirely. This process is probably most efficient in systems with multiple giant planets, where close encounters are more likely. The planet that gets ejected carries away angular momentum, helping the remaining planets settle into more stable orbits. It's a violent process, but it serves a purpose in the architecture of the system left behind. The second formation mechanism is more subtle. Some rogue planets might never have been part of a planetary system at all. They might form directly from the collapse of gas clouds the same way brown dwarfs and stars form, but in regions where the available mass is too small to create anything more massive than a planet. These objects blur the line between planets and stars. They're not ejected, they're simply born alone. Scientists call them sub-brown dwarfs, or planetary mass objects, though the terminology is still debated. The distinction matters because it tells us something about the definition of a planet. Is a planet defined by how it forms by being part of a planetary system, or is it defined by its mass and composition regardless of where it came from? The International Astronomical Union's definition of a planet includes the requirement that it orbits a star, which would exclude rogue planets by definition. But that seems arbitrary. If an object has the mass composition and internal structure of a planet, does it stop being a planet just because it's no longer orbiting anything? Imagine what life would be like on a rogue planet if life could somehow exist there. The sky would be black, truly black, not the dark blue of Earth's night sky lit by scattered sunlight, but the pure black of deep space. Stars would be visible, countless stars, more than you could ever see from Earth, because there's no atmosphere to scatter light or block faint objects. The Milky Way would arc overhead like a river of light, and distant galaxies might be visible to the naked eye, tiny smudges against the dark. But there would be no warmth from any star. The surface temperature would be determined only by internal heat left over from the planet's formation, and heat generated by radioactive decay in the core. For a large rocky planet like Earth, this internal heat is minimal. Earth's core is hot, but that heat doesn't reach the surface in significant amounts. A rogue Earth would freeze solid within a few million years, its oceans turning to ice kilometers thick, its atmosphere condensing and snowing down onto the frozen surface. However, some scientists suggest that life could potentially survive on a rogue planet under the right conditions. If the planet is large enough to retain a thick atmosphere, that atmosphere could act as an insulating blanket trapping internal heat and keeping subsurface oceans liquid. Jupiter's moon, Europa and Saturn's moon, Enceladus, both have subsurface oceans heated by tidal forces and internal radioactive decay, no sunlight required. A large rogue planet with a thick hydrogen atmosphere could create a greenhouse effect, strong enough to maintain liquid water beneath the ice powered entirely by internal heat. It would be a strange biosphere if it existed. No photosynthesis since there's no light. All energy would come from chemical processes, from heat gradients, from the slow decay of radioactive elements, from whatever chemistry the planet's interior makes possible. Life would be slow, quiet, efficient, adapted to darkness and scarcity. But it wouldn't be impossible. Earth has ecosystems that survive without sunlight, clustered around hydrothermal vents on the ocean floor, living on chemical energy released by volcanic activity. the same principle could work on a rogue planet. Different circumstances, same fundamental chemistry. One of the fascinating aspects of rogue planets is their potential role in panspermia, the hypothesis that life could spread from one world to another. If a planet is ejected from its system while it still hosts life, that life might survive the journey through interstellar space protected by thick ice and insulated by the planet's atmosphere. Billions of years later, the rogue planet could be captured by another star system, bringing its frozen biosphere into a new environment where heat from a new sun could thaw the ice and revive dormant organisms. It's speculative, but the physics allows for it. Research published in astrobiology has explored the possibility that Earth itself might have been seeded by organisms from a rogue planet that passed through the early solar system. It's unlikely, but not impossible. Life is resilient. Microorganisms have survived in Earth's upper atmosphere in the vacuum of space on the outside of the International Space Station, in the frozen Antarctic ice for millions of years. If life can endure those conditions, maybe it can endure the cold dark of a rogue world's journey. There's something poetic about rogue planets, isn't there? Outcasts, wanderers, free from the gravitational chains of a star, but also cut off from the warmth and light that stars provide. They trade stability for freedom, orbit for isolation. They're the hermits of the galaxy drifting through the void with nothing but time and darkness and whatever they carry within themselves. Detecting rogue planets remains difficult, but technology is improving. The Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, will conduct a large microlensing survey that could detect thousands of rogue planets, including some as small as Mars. By cataloging these objects, scientists hope to understand how common they are, how they're distributed across the galaxy, and what that tells us about the efficiency of planetary ejection processes. One surprising discovery is that some rogue planets might not be completely alone. Computer simulations suggest that when a planet is ejected from a system, it could carry moons with it. If the ejection happens slowly enough, moons in close orbits might remain bound to the planet, continuing to orbit even as the planet leaves its star behind. A rogue planet with a large moon would have tidal heating friction generated by gravitational interactions between the planet and moon, similar to what keeps Europa and Enceladus warm. This tidal heating could provide enough energy to maintain subsurface oceans for billions of years, creating stable environments where life might emerge and persist. It seems as though the universe finds ways to create habitable niches in the most unexpected places. We think of habitability as requiring a star, but maybe stars are just one solution to the energy problem. Maybe there are other solutions, other sources of heat and light and chemical energy, other ways for worlds to remain active and warm and alive without orbiting anything. There's also a statistical argument for taking rogue planets seriously in the search for life. If there are truly more rogue planets than stars, and if even a tiny fraction of them have conditions that could support life, the total number of potentially habitable environments in the galaxy could be much larger than we thought. We've been searching for life on planets and habitable zones around stars, but we've ignored the vast population of worlds drifting in the dark. Maybe that's where we should be looking. Maybe isolation is not a barrier to life, but a different kind of opportunity. One common mistake in thinking about rogue planets is assuming they're all cold and dead. While most are probably frozen and lifeless, the largest ones, super-Earths and sub-brown dwarfs, could retain significant internal heat for billions of years. They might have atmospheres thick enough to create greenhouse effects, surfaces warm enough for exotic chemistry, even lightning storms powered by convection in their dense atmospheres. Some theoretical models suggest that the largest rogue planets could have surface temperatures above freezing, purely from internal heat and atmospheric insulation, creating environments that are dark but not frozen. Another misconception is that rogue planets are rare. The evidence suggests the opposite. They might be the most common type of planet in the galaxy. We just can't see them easily, so we've overlooked them. It's a reminder that absence of evidence is not evidence of absence. The universe is full of things we haven't detected yet, not because they don't exist, but because we haven't figured out how to look for them properly. Think about what it means that there could be trillions of planets drifting through our galaxy alone, unseen, uncounted, carrying their own histories of formation and ejection, their own internal warmth slowly fading across deep time. Each one is a world as real as Earth, with geology and chemistry and weather, maybe even life, all happening in the dark where no telescope can see. The galaxy is not just the stars and the planets that orbit them. It's also the invisible majority, the rogues, the wanderers, the ones that got away. As we continue our drift through strangeness, we'll turn our attention to worlds that remain bound to stars, but live in conditions just as extreme as the rogues. Planets where the oceans are not water, but something stranger. Planets where the ground beneath you flows and glows with heat, where the entire surface is molten, where liquid rock rains from the sky, and rivers of lava carve channels through landscapes that never cool. Worlds of fire and flow where solidity is the exception and everything moves. Imagine standing on a shore where the ocean stretches to every horizon, not just in front of you, but in every direction, because there is no land. Just water hundreds of kilometers deep, covering the entire planet, like a blanket wrapped around a world that never asked to be drowned. Or imagine the opposite, standing on a cliff of solid rock, overlooking an ocean that glows orange and red, an ocean not of water, but of molten stone, flowing and churning with currents driven by heat from below waves of liquid rock, crashing against shores that melt and reform with each tide. Both of these worlds exist out there, extremes of liquid that make Earth's oceans seem ordinary, balanced, almost cautious by comparison. Water is strange. We forget that because it's everywhere on Earth, so familiar it seems normal. But water's properties are unusual, almost improbable. It's one of the few substances that expands when it freezes, which is why ice floats. It has an exceptionally high heat capacity, meaning it absorbs and releases large amounts of energy without changing temperature much, which stabilizes Earth's climate. It's a universal solvent, dissolving more substances than almost any other liquid, which makes it essential for the chemistry of life. And it exists in all three states, solid, liquid, and gas, within the relatively narrow temperature range found on Earth's surface. Because water is so important here, we've assumed it's important elsewhere. The search for extraterrestrial life has been largely a search for liquid water. Where there's water, we think there might be life. It's a reasonable hypothesis based on the only example we have. But the universe doesn't always follow our logic. Sometimes it takes our assumptions and twists them into forms we never imagined. GJ1214b was discovered in 2009 orbiting a red dwarf star about 48 light-years from Earth in the constellation Ophiuchus. It's classified as a super-Earth, roughly 2.7 times Earth's radius, and about 8 times Earth's mass. Early observations showed it transits its star passing in front of it from our perspective, which allowed scientists to measure its size precisely. But when researchers calculated its density based on mass and radius, something seemed off. The density was too low to be a rocky planet like Earth, too low even to be a smaller gas giant like Neptune. Scientists suggested that GJ1214b might be a water world, a planet with an enormous global ocean covering a small rocky core. Models indicate the ocean could be hundreds of kilometers deep, far deeper than Earth's oceans, which average only about 4 kilometers in depth. On J1214b, there might be no seafloor at all. In the traditional sense, just water getting denser and hotter as you descend, eventually transitioning into exotic high-pressure phases of ice that only exist under extreme conditions. Wait ice at high temperatures. That seems contradictory, but it's real. Water ice exists in multiple crystalline structures depending on temperature and pressure. On Earth, we're familiar with Ice 1, the ordinary ice that forms in your freezer or on a winter pond. But at higher pressures, water forms, Ice 2, Ice 3, Ice 5, Ice 6, Ice 7, and more, each with a different crystal structure. Some of these high-pressure ices remain solid at temperatures above the boiling point of water at Earth's surface. On a water world like GJ 1214b, the ocean would be layered liquid water near the surface and deeper down, hot ice under pressures measured in millions of atmospheres. Research published in the Astrophysical Journal explored what the interior structure of such a world might look like. At the very center, a rocky or metallic core, perhaps only a few thousand kilometers in diameter. Surrounding that, a mantle of high-pressure ice, Ice 7 or Ice 10, compressed into crystalline solids, despite temperatures that could exceed 1,000 degrees Celsius. Above that, a thick layer of liquid water, and at the surface, an atmosphere of steam and hydrogen, thick and hazy, scattering light and making the planet difficult to observe. The Hubble Space Telescope studied GJ 1214b's atmosphere using transmission spectroscopy, analyzing how starlight filters through the atmosphere during transits. The data showed a relatively featureless spectrum, suggesting the atmosphere is dominated by water vapor or obscured by high-altitude clouds or hazes. Either way, it confirmed that this planet is unlike anything in our solar system. It's not a gas giant. It's not a rocky world. It's something in between a category we didn't have a name for until we found it. Later, discoveries added more candidates to the water world category. TOI 1452, B announced in 2022, orbits a red dwarf about 100 light-years away. It's slightly larger and more massive than Earth, and its density suggests it could be composed of up to 30% water by mass. For comparison, Earth is only about 0.02% water by mass. Most of our planet is rock and iron. On TOI 1452, B water dominates. If you could visit, you would find yourself in a world where solid ground is a rare exception, if it exists at all. Everything is ocean. Living on a water world would require completely rethinking what habitation means. There would be no continents, no islands, no shallow seas where life could emerge from water onto land. All life, if it existed, would be aquatic. There would be no place to build cities unless you built them floating or submerged. No agriculture unless you cultivated kelp or algae. No mining unless you could somehow drill through kilometers of water to reach the rocky core below. But maybe that's not a disadvantage. Earth's oceans are full of life, diverse and abundant, even in the deepest trenches where sunlight never reaches. A water world might be an ideal environment for life, not despite the lack of land, but because of it. Water protects against radiation. Moderate temperature provides a medium for chemical reactions and allows organisms to move in 3 dimensions instead of being confined to a 2-dimensional surface. Perhaps we're the strange ones living on a planet that's mostly rock and water. Worlds are the norm. Scientists estimate that water worlds might be relatively common in the galaxy. Many of the super-Earths we've discovered have densities consistent with significant water content. If planets form beyond the frost line, the distance from a star where water can freeze and then migrate inward, they would carry their ice with them. As they get closer to the star, that ice melts, creating deep global oceans. It's a plausible formation scenario, and the observations support it. Now, let's turn to the opposite extreme. Not worlds covered in water, but worlds covered in molten rock, lava planets, places where the ground itself flows, where the surface is not solid, but liquid glowing with heat, constantly renewed by convection from the interior. K2141b was discovered by the Kepler Space Telescope's K2 mission and studied in detail by researchers who published their findings in monthly notices of the Royal Astronomical Society in 2020. This planet is about 1.5 times Earth's size and orbits a star about 200 light-years away, but its orbital period is less than 7 hours. 7 hours. It circles its star faster than Earth rotates once. At that distance, the surface temperature on the day side reaches about 3,000 degrees Celsius, hot enough to vaporize rock. Scientists modeling K2141b's climate propose something extraordinary. The planet likely has a lava ocean on the day side, a sea of molten rock hundreds of meters deep. The heat vaporizes the lava, creating an atmosphere of rock vapor, silicon monoxide, sodium, potassium, all materials that would be solid at Earth's temperatures. This rock vapor is carried by winds toward the cooler night side, where it condenses and falls as rain. But not water rain. Rock rain. Tiny droplets of molten stone precipitating from clouds of vaporized minerals. The rain collects on the night side, where it's still hot enough to remain liquid and flows back toward the day side in lava rivers, completing a cycle that mirrors Earth's water cycle, but with entirely different materials. Evaporation, condensation, precipitation, runoff. The same processes, the same physics, just at temperatures that would incinerate anything we know. It's as if the planet is breathing circulating rock through its atmosphere, the way Earth circulates water. Think about what that means. Weather made of stone, clouds of vaporized basalt, storms where the lightning arcs through air, thick with silicon compounds, and the thunder shakes ground that flows like a slow river. It defies every intuition we have about how planets work, and yet, the physics is straightforward. Heat creates vapor. Vapor moves, vapor cools, and condenses. The material changes, but the pattern remains. Corot 7. B, discovered in 2009, was one of the first rocky exoplanets ever confirmed. It orbits a star about 500 light-years away, completing one orbit every 20 hours. Early estimates of its surface temperature suggested it could exceed 2,000 degrees Celsius on the day side, hot enough to melt rock. Scientists propose that this planet might have lakes or seas of lava regions where the surface is molten, surrounded by areas where the rock has cooled enough to form a solid crust. Research shows that Corot 7b likely experiences extreme volcanic activity driven by tidal heating. The planet's orbit is slightly eccentric, meaning its distance from the star varies slightly over each orbit. This variation creates tidal forces that flex the planet's interior, generating heat through friction. The same process heats Jupiter's moon, Io, the most volcanically active body in our solar system. But on Corot 7b, the tidal heating would be much more intense, creating a surface in constant flux, erupting and melting and reforming in cycles measured in hours or days. Imagine trying to map a world like that. Every time you observe it, the surface has changed. Lava flows have cooled and new ones have erupted. Volcanic vents open and close. The geography is temporary fluid, never the same twice. There would be no permanent features, no mountains that last for millions of years, no craters that record ancient impacts. Everything is erased and rewritten constantly by the heat. One of the lessons from studying lava planets is about the diversity of geological processes. On Earth, geology is driven by plate tectonics, volcanic activity, erosion, and sedimentation. These processes operate over millions of years, slowly reshaping the surface. On a lava planet, geology operates on timescales of hours or days. The planet's surface is not a stable platform, but an active interface between the interior and space, constantly exchanging material and energy. Scientists also study these worlds to understand the early Earth. When Earth first formed about 4.5 billion years ago, it was much hotter than it is now. The surface might have been partially molten, a magma ocean covering the young planet. Studying lava planets gives us a window into what Earth might have looked like in its infancy, before it cooled enough for solid continents to form, before water condensed from the atmosphere to create the first oceans. There's also a question about habitability. Obviously, a lava planet with a molten surface is not habitable for life, as we know it. But what about moons orbiting lava planets? If a large lava planet has moons in stable orbits, those moons would receive intense infrared radiation from the planet's glowing surface. Depending on their distance and the planet's temperature, some of that heat could warm the moons enough to maintain liquid water, even if the moons orbit far from the star. It's speculative, but it's another reminder that habitability is context-dependent. The contrast between water worlds and lava planets illustrates something fundamental about planetary diversity. Both are covered in liquids, but those liquids are as different as possible. Water is life-giving, temperate, stable. Lava is destructive, extreme, chaotic. Yet both emerge from the same basic physics, the same processes of heat, gravity, chemistry, and time. The universe doesn't have preferences. It just creates every possible variation and lets them exist. On Earth, we have both water and lava, but they're segregated. Water covers 70% of the surface, while lava is mostly confined to volcanic regions and the deep interior. We have balance moderation, a separation between the liquid that supports life and the liquid that would destroy it. But out there among the thousands of exoplanets, balance is rare. Most worlds pick an extreme and commit to it fully. Have you ever considered how fragile Earth's balance really is? We orbit at exactly the right distance from the sun to keep water liquid. Too close, and we'd be a lava world. Too far, and we'd be a frozen ice ball. The range is narrow, and we're right in the middle of it. Some scientists call it the Goldilocks zone. Not too hot, not too cold, just right. But finding water worlds and lava planets reminds us that Goldilocks is the exception. Most planets are either too hot or too cold, too wet, or too dry, too dense, or too thin. Earth is the lucky accident. As we prepare to drift further, we'll encounter another kind of strangeness, not about what covers a planet, but about what the planet is made of, about density and mass, and the strange physics that emerges when gravity pulls matter together in unexpected ways. We'll meet planets lighter than cork and planets heavier than lead, worlds that challenge our understanding of what's even possible when you gather enough atoms in one place and let gravity do its work. What if I told you there's a planet out there the size of Jupiter, but light enough that it would float in water if you could somehow find an ocean large enough to test it? Or another world smaller than Neptune, but so dense, so compressed by its own gravity that a handful of its material would weigh more than a car. Density is one of those properties we don't think about much on Earth, because everything here falls within a familiar range. Rock is heavy, water is medium, air is light. Simple, predictable. But the universe has found ways to create planets that break every rule we thought governed how matter behaves when you gather enough of it in one place. Density is just mass divided by volume, how much stuff is packed into how much space. On Earth, the average density is about 5.5 grams per cubic centimeter, mostly because of our iron core. Water, by comparison, is 1 gram per cubic centimeter. Saturn, the least dense planet in our solar system, averages about 0.69 grams per cubic centimeter, less dense than water, which means Saturn would float if you could find a bathtub big enough, though the ring system might complicate things. But these densities make sense given what the planets are made of. Rock and metal are dense. Hydrogen and helium are not. Mix them in different proportions and you get different average densities. The strange part is when we find planets that don't follow this logic. Planets that are too light for their size or too heavy for their composition. Planets that seem to violate the patterns we've observed in our own solar system, forcing us to reconsider what we thought we understood about planetary structure. WASP 107b was discovered in 2017, orbiting a star about 212 light-years from Earth in the constellation Virgo. It's slightly smaller than Jupiter in radius, but has only about 1/10 of Jupiter's mass. When astronomers calculated its density, they found it was extraordinarily low, roughly 0.13 grams per cubic centimeter. Lighter than cotton candy, lighter than styrofoam, almost as light as air. It's one of the least dense planets ever discovered, a world so fluffy it challenges our understanding of how planets hold themselves together. How does a planet become this insubstantial? The answer lies in its atmosphere. Research shows that WASP-107b has an enormously extended atmosphere, a thick envelope of hydrogen and helium that makes up a huge fraction of the planet's total mass. The core, the solid or liquid center where heavier elements might exist, is relatively small, perhaps only 4 to 5 Earth masses. Everything else is gas puffed up by heat from the nearby star, and by internal processes we're still trying to understand. One hypothesis is that WASP-107b is losing mass continuously. The planet orbits very close to its star, completing one orbit in about 5.7 days. At that distance, the star's radiation heats the upper atmosphere to thousands of degrees, giving gas molecules enough energy to escape the planet's gravity. Scientists call this atmospheric escape, or evaporation. Over time, the planet is slowly boiling away into space, shedding its outer layers like a slow-motion explosion. Models suggest WASP-107b could lose about 0.1% of its total mass every billion years, which might not sound like much, but over the age of the solar system that adds up. The Hubble Space Telescope and the James Webb Space Telescope have both observed WASP-107b in detail, analyzing its atmosphere during transits. The data revealed water vapor, methane, carbon dioxide, and traces of other molecules, confirming that the atmosphere is not just hydrogen and helium, but contains heavier elements mixed throughout. This tells us something important about how the planet formed. It probably didn't start out this light. It likely had more mass initially, and atmospheric escape has been stripping away the outer layers, leaving behind this strange puffy remnant. But there's another factor contributing to WASP-107b's low-density tidal heating. The planet's orbit is slightly eccentric, not perfectly circular, which means its distance from the star varies over each orbit. This creates tidal forces that squeeze and stretch the planet, rhythmically generating heat through friction in the interior. This heat causes the atmosphere to expand, making the planet larger for its mass, lowering its density even further. It's like heating a balloon. The amount of gas inside doesn't change, but the volume increases as the gas expands. Think about what it would be like to descend through WASP-107b's atmosphere, if such a journey were possible. You'd start in the thin upper layers, where hydrogen molecules are so sparse they barely interact. Gradually, as you descend, the atmosphere would thicken, pressure and temperature would rise. You'd pass through cloud layers, perhaps made of silicates or other condensates, though we're not sure exactly what materials would condense at these temperatures and pressures. Deeper still, the hydrogen would become denser, transitioning from a gas to a supercritical fluid, a state where the distinction between liquid and gas breaks down. Eventually, you'd reach the core, if there is a distinct core, a small rocky center buried under thousands of kilometers of atmosphere. It's a world with no surface in the traditional sense, just layers of gas getting denser as you go deeper, until pressure turns gas into something else entirely. You couldn't land on it. You could only sink through it until the pressure crushed whatever vessel you were in. Now, let's turn to the opposite extreme planets that are far denser than they should be. TOI 849b was discovered by the TESS mission and announced in 2020. It's about 3.4 times Earth's radius, placing it in the Neptune-size range, but its mass is about 40 times Earth's mass. When scientists calculated its density, they found it was exceptionally high, about 5.5 grams per cubic centimeter, similar to Earth's density, which is strange for a planet that size. Planets the size of Neptune are usually gas giants with thick hydrogen and helium atmospheres, surrounding relatively small, rocky or icy cores. But TOI 849b doesn't fit that pattern. Its high density suggests it's almost entirely core with little to no atmosphere. It's as if someone took a gas giant and stripped away all the gas, leaving only the dense center behind. Scientists call it a stripped core or a Chthonian planet, a term borrowed from Greek mythology referring to gods of the underworld, beings that exist beneath the surface. How does this happen? One scenario is that TOI 849b was once a much larger gas giant, perhaps similar to Jupiter, but something catastrophic removed its atmosphere. It could have been a collision with another planet early in the system's history, a violent impact that blasted away the outer layers and left the core exposed. Or it could have been photoevaporation, the process where intense radiation from the star heats the atmosphere so much that it escapes into space. Over hundreds of millions of years, the planet loses its entire gaseous envelope, leaving behind only the solid interior. Another possibility is that TOI 849b never finished forming. Planetary formation is a process that happens over millions of years. Gas giants form by first building a solid core through accretion of rock and ice. And once that core reaches about 10 Earth masses, it becomes massive enough to gravitationally capture large amounts of hydrogen and helium from the surrounding protoplanetary disk. But if something disrupts this process, if the disk dissipates before the planet finishes accreting gas, you're left with just the core, a massive rocky world with no atmosphere. Research published in Nature suggests that TOI 849b is in the process of forming or has recently had its atmosphere stripped because its orbit is very close to its star, completing one revolution in just 18 hours. At that distance, any atmosphere would be subject to intense heating and tidal forces, making it difficult for the planet to retain gas. The fact that it exists as an exposed core gives scientists a rare opportunity to study the interior structure of what would normally be hidden beneath thick layers of atmosphere. The density of TOI 849b tells us it's composed primarily of rock and metal, with relatively little ice or volatile materials. This high metal content suggests it formed in the inner regions of its planetary system, where temperatures were high enough to prevent ice from condensing. It's like Earth in that respect, a terrestrial composition despite its much larger size. If you could stand on its surface assuming it is cooled enough to have a solid surface, you'd experience gravity about 5 times stronger than Earth's. Walking would be exhausting. Every step would feel like carrying a backpack full of bricks. One of the fascinating aspects of studying extreme density planets is what they reveal about planetary interiors. On Earth, we can't directly observe the core. It's buried thousands of kilometers below the surface, inaccessible to drilling or direct sampling. Everything we know about Earth's interior comes from indirect methods, seismic waves, gravitational measurements, magnetic field studies. But planets like TOI 849b are essentially exposed cores, and by studying their properties, we can learn about what planetary cores are made of and how they behave. Scientists use observations of density to constrain models of interior structure. If you know a planet's mass and radius, you can calculate its average density, and from that, you can infer the proportions of rock, metal, ice, and gas that make up the planet. High density implies lots of rock and metal. Low density implies lots of gas or ice. It's detective work, piecing together a picture of the unseen interior based on measurements of the whole. There's also a category of planets called super-Earths that fall between Earth and Neptune in size but show a wide range of densities. Some super-Earths are rocky with densities similar to Earth's, suggesting they're scaled-up versions of terrestrial planets. Others are much less dense, suggesting they have thick atmospheres or significant amounts of water or ice. The diversity is striking. Just because two planets have similar sizes doesn't mean they have similar compositions or formation histories. Kepler 10c, discovered in 2014, is a super-Earth about 2.3 times Earth's radius and roughly 17 times Earth's mass. When it was first characterized, scientists suggested it might be a mega-Earth, an extremely massive rocky planet, which would make it one of the densest exoplanets known. However, later observations and reanalysis of the data introduced uncertainty about its mass, and the current best estimate suggests it might be less massive than initially thought, which would make it less dense and possibly more Neptune-like. This highlights a challenge in exoplanet science. Measurements have uncertainties, and sometimes those uncertainties are large enough to change our interpretation of what a planet is. Have you ever thought about what determines a planet's density in the first place? It comes down to three main factors. First, composition. Heavy elements like iron and nickel are denser than lighter elements like hydrogen and helium. A planet made mostly of iron will be denser than a planet made mostly of gas. Second, temperature. Heat causes materials to expand, decreasing density. A hot planet of the same composition as a cool planet will be less dense because the atoms are moving faster and taking up more space. Third, pressure. Gravity compresses the interior of large planets, increasing density. The core of Jupiter is much denser than the core of Earth, not because it's made of different materials necessarily, but because the weight of all the overlying layers compresses it to extreme densities. These three factors interact in complex ways. A planet's temperature depends on its distance from the star, its internal heat production, and its atmospheric greenhouse effect. Its pressure depends on its mass and radius. Its composition depends on where and how it formed. Change any one variable, and you change the density. The universe explores this parameter space, freely creating every possible combination. And we're left trying to catalog and understand the results. One common misconception is that larger planets are always more massive. That's true in general, but there are exceptions. WASP-1 07b is larger than many planets that are far more massive. Size and mass don't always correlate perfectly because density varies so much. A planet can be physically large, but contain relatively little matter if it's mostly gas. Conversely, a planet can be small but incredibly massive if it's composed of dense materials and compressed by gravity. Another lesson from studying density extremes is about planetary evolution. Planets are not static. They change over time. They lose atmospheres, they cool, they get bombarded by asteroids. They migrate to different orbits. The planet we observe today might be very different from the planet that formed billions of years ago. WASP-1 07b is probably losing mass right now, slowly deflating. TOI 849 b might have once been a gas giant and is now just a remnant. Planetary science is not just about describing what planets are, but about understanding what they were and what they're becoming. As we move forward through this cosmic gallery of strangeness, we'll shift our perspective from the physical properties of planets to their place in time. We'll meet worlds that are almost as old as the universe itself, ancient wanderers that have seen the galaxy change and grow around them, and we'll meet worlds still in the process of being born, newborn giants glowing with the heat of formation, surrounded by the dusty disks from which there's still accreting mass. Time itself becomes strange when you think on these scales. Imagine a planet that existed before our sun was born, a world that orbited its stars when the universe was less than 1 billion years old, when the first galaxies were still forming, when the chemistry of space was simpler and stranger than it is now. Or imagine standing near a planet still wrapped in the glowing disk of gas and dust from which it's forming, watching in real time as gravity pulls matter together as a world builds itself from chaos and cloud. Time becomes strange when you realize some planets are older than almost everything else in existence, while others are so young, they're still being shaped by the forces that created them. The universe is 13.8 billion years old. That's not a guess anymore, but a measurement derived from observations of the cosmic microwave background, the afterglow of the Big Bang itself. Everything we see, every star, every galaxy, every planet, formed sometime after that initial moment of expansion. But not everything formed at the same time. The first stars ignited perhaps 100 million years after the Big Bang, massive and short-lived burning, through their fuel quickly and exploding as supernovae. Those explosions seeded space with heavier elements, carbon, oxygen, iron, silicon, all the materials needed to build rocky planets. But in the earliest epochs before enough generations of stars had lived and died, the universe was mostly hydrogen and helium, with only trace amounts of anything heavier. Conventional wisdom suggested that planets, especially rocky planets, couldn't form in such an element-poor environment. Without enough heavy elements, you couldn't build substantial cores, and without cores, you couldn't capture gas to make gas giants. Planet formation scientists assumed had to wait until the universe was older, more chemically enriched, more capable of supporting the complex processes that create worlds. Then we found PSRB 162-0-26b, and conventional wisdom had to be revised. This planet orbits a binary system consisting of a pulsar and a white dwarf located in the globular cluster Messier 4, about 12,000 light-years from Earth. Globular clusters are ancient densely packed groups of stars that formed in the early universe. Messier 4 is estimated to be about 12.7 billion years old, making it one of the oldest structures in our galaxy. The planet orbiting this binary system is estimated to be almost as old as the cluster itself, roughly 12.7 billion years, give or take a few hundred million. When this planet formed, the universe was only about 1 billion years old. Earth wouldn't exist for another 8 billion years. The Sun wouldn't exist. The Milky Way was still assembling itself from smaller galaxies. And yet somehow this planet came into being a survivor from an era we can barely comprehend. The discovery was made using pulsar timing, a technique that measures the precise intervals between pulses emitted by a pulsar, a rapidly rotating neutron star that sends out beams of radiation like a cosmic lighthouse. Any object orbiting the pulsar affects the timing of these pulses through gravitational interactions. By analyzing tiny variations in the pulse arrival times, astronomers detected not just the white dwarf companion, but also a planetary mass object orbiting both stars in a wide orbit, completing one revolution about every 100 years. Research suggests the planet is about 2.5 times Jupiter's mass, making it a gas giant. But how did it form in an environment with so few heavy elements? Scientists propose several scenarios. One possibility is that the planet originally formed around one of the stars before it became a pulsar back when it was a normal main sequence star. When that star exhausted its fuel and exploded as a supernova, the planet somehow survived the blast, remaining in orbit around the remnant neutron star. Later, the neutron star captured the white dwarf as a companion, or perhaps they were always a binary system and both stars evolved while the planet remained. Another possibility is that the planet formed later after one or both stars had already evolved from material ejected during the stellar evolution process. This seems less likely, but it's not impossible. The universe finds ways to create planets in environments we'd consider hostile or impossible. What strikes me most about PSRB 162-0-26b is the sheer duration of its existence, 12.7 billion years. That's long enough for entire galaxies to form, for countless generations of stars to be born and die, for the universe to expand and cool and change in fundamental ways. This planet has witnessed almost the entire history of the cosmos. If it could somehow remember, it would have seen the universe when it was young and bright and different. It would have seen the Milky Way coalesce, seen the sun ignite, seen Earth form and life emerge, and civilizations rise all from its distant orbit around ancient dying stars. Time at that scale becomes almost meaningless to us. We measure our lives in decades, human history in thousands of years, geological time in millions or billions of years. But 12.7 billion years. That's 85% of the universe's total age. It's hard to wrap your mind around it, hard to feel the weight of that duration. Scientists sometimes refer to PSRB 1620-26b as Methuselah, after the biblical figure said to have lived 969 years, a metaphor for extreme age. It's a fitting name for the oldest known planet, a relic from a time when the universe was fundamentally different, when stars were made of different stuff, when the chemistry of space hadn't yet been enriched by supernovae. One lesson from Methuselah is that planet formation is more robust than we thought. Even in environments with very low metallicity, the astronomical term for elements heavier than hydrogen and helium planets can form. This has implications for the search for life. If planets can exist in the early universe, and if some of those planets are in habitable zones, then life might have had much longer to develop than we assumed. There could be biospheres out there that are billions of years older than Earth's civilizations that arose when our galaxy was young. Of course, there's a counter-argument. The early universe had less heavy elements, which means fewer rocky planets, and rocky planets are thought to be more suitable for life than gas giants. Also, the early universe was more violent with higher rates of supernovae and active galactic nuclei, both of which produce radiation that could sterilize nearby planets. So, while planets could exist, habitability might have been rare. We don't know yet. But the existence of ancient planets opens possibilities we're only beginning to explore. Now, let's turn to the opposite end of the timeline: planets, so young they're still forming. PDS-70 is a star about 370 light-years from Earth, roughly 5 million years old, which in stellar terms is incredibly young. Our Sun, by comparison, is about 4.6 billion years old. PDS-70 is still surrounded by a protoplanetary disk, a thick cloud of gas and dust left over from the star's formation. And within that disk, astronomers have directly observed planets in the process of forming. PDS-70b and PDS-70c are two gas giants orbiting within gaps they've carved in the disk. These gaps are visible in images taken by the SPHERE instrument on the Very Large Telescope and by the ALMA radio telescope array. The planets are accreting material from the disk, pulling in gas and dust, growing in mass as we watch. Research published in Nature Astronomy in 2018 confirmed that PDS-70b is actively accreting with material falling onto the planet and heating up as it does, causing the planet to glow brightly in infrared light. This is extraordinary. We're observing planet formation in real time, not piecing it together from models or simulations, but actually watching it happen. The planets are a few million years old at most, which means they're still in their infancy, still accumulating the mass they'll carry for the rest of their existence. Imagine being present at the birth of a world, witnessing the moment when scattered dust becomes a coherent object, when gravity wins and a planet emerges from the chaos. Scientists estimate that PDS-70b is about 5 to 9 times Jupiter's mass, while PDS-70c is somewhat smaller. Both orbit relatively far from their star, PDS-70b at about 20 astronomical units, roughly the distance of Uranus from the Sun, and PDS-70c at about 34 astronomical units beyond Neptune's orbit. They're still embedded in the disk, still surrounded by the material they're accreting, still growing. One of the most fascinating discoveries is that PDS-70c has its own circumplanetary disk, a smaller disk of material orbiting the planet itself. This is where moons form. We're watching not just a planet being born, but the beginnings of a moon system, a multi-layered process of formation, happening at different scales simultaneously. It's like watching a solar system assemble itself layer by layer, object by object, from the inside out. The protoplanetary disk around PDS-70 won't last forever. Models suggest that disks typically dissipate within about 10 million years, dispersed by stellar winds, accreted onto planets, or blown away by nearby supernovae. Once the disk is gone, planet formation stops. The planets that exist at that point are the planets that will remain, though they might still migrate, collide, or get ejected. the system settles into a more stable configuration, and the chaotic early phase ends. This raises an interesting point about timing. If we had observed PDS 70 a few million years earlier, we might have seen only a disk with no visible planets yet. If we observe it a few million years in the future, the disk might be gone and the planets fully formed. We're catching this system at exactly the right moment to see planet formation in progress. It's lucky in a way. The universe is vast, but the windows for observing certain processes are narrow. We happen to look at the right place at the right time. Studying young planets like those in the PDS 70 system helps us understand how our own solar system formed. When the Sun was young, it was surrounded by a similar protoplanetary disk. Jupiter, Saturn, Uranus, and Neptune formed within that disk, carving gaps migrating inward or outward, interacting gravitationally. The rocky planets, Mercury, Venus, Earth, and Mars, formed closer to the Sun, where temperatures were high enough that only rock and metal could condense. Over millions of years, the disk cleared, and the solar system as we know it emerged. But there are differences too. The PDS 70 planets are more massive than Jupiter and orbit farther from their star than any planet in our solar system except Neptune. This suggests that planet formation is not a one-size-fits-all process. Different systems produce different outcomes, depending on the mass of the disk, the composition of the material, the presence of nearby stars, and countless other factors. Every planetary system is unique, shaped by its own particular history. Another young planetary system worth mentioning is Beta Pictoris, a star about 63 light-years away and only about 23 million years old. It has a prominent debris disk, a disk made mostly of dust and small particles rather than the gas-rich protoplanetary disks around even younger stars. Within this disk, astronomers have directly imaged at least two planets, Beta Pictoris b and Beta Pictoris c, both gas giants. These planets are young enough that they're still glowing with heat from their formation, making them easier to detect in infrared light. Beta Pictoris b is particularly interesting because its orbit carries it through the disk, causing periodic changes in the disk structure as the planet's gravity stirs up the material. Observations over multiple years have tracked the planet's motion, confirming its orbital period of about 20 to 21 years. It's one of the few exoplanets whose orbit we've watched over a significant fraction of its period, giving us direct measurements of its trajectory and mass. What does it mean for a planet to be young? It means the planet is still contracting, still radiating heat left over from its formation. When gas giants form, the process of pulling material together releases gravitational potential energy, heating the interior. This heat takes millions or even billions of years to radiate away. Young gas giants are hot, glowing luminous. As they age, they cool and dim. Jupiter still radiates more heat than it receives from the Sun, a remnant of its formation 4.6 billion years ago. PDS 70b and PDS 70c are much hotter, much brighter, because they're so much younger. For rocky planets, youth means something different. A young rocky planet might still have a molten surface, a magma ocean, that takes time to cool and solidify. Earth went through this phase. When it first formed, the surface was likely molten, kept liquid by the heat of accretion and by impacts from asteroids and other debris. Over tens of millions of years, the surface cooled enough for a solid crust to form, and eventually water vapor in the atmosphere condensed to create the first oceans. Young rocky planets are violent, unstable, constantly reshaped by impacts and volcanic activity. One common mistake people make is thinking that planets form quickly in a cosmic instant. In reality, planet formation takes millions of years. The initial collapse of the protoplanetary disk might happen relatively quickly, but the accretion of material onto growing planets is a slow process. Particles stick together through static electricity and weak gravitational attraction, building up over time. It's gradual, incremental, patient. The universe doesn't rush. There's also a misconception that once a planet forms, it's done static and unchanging. But planets evolve. They cool, they lose atmospheres, they get hit by asteroids, they migrate to new orbits. A planet is not a finished product, but a work in progress, shaped by its environment and its history. The PDS-70 planets will change as they age. They will cool, their atmospheres will settle, their orbits might shift. The planets we see now are not the planets they will be in a billion years. Comparing the oldest and youngest planets gives us a sense of the vast range of planetary ages in the universe. PSRB 1620-26 Base E has existed for 12.7 billion years, while PDS-70b and PDS-70c are only a few million years old. The age difference is nearly 3 orders of magnitude, a factor of more than 1,000. It's like comparing a newborn baby to someone who's been alive for thousands of years, except the time scale is billions of years instead of decades. And here's something to consider. If intelligent life exists on any of these ancient worlds, or on planets we haven't discovered yet that are similarly old, those civilizations could be billions of years ahead of us. They could have technologies we can't imagine, understandings of physics we haven't even begun to explore. Or they could have already risen and fallen, leaving behind ruins or remnants, or nothing at all, their existence forgotten in the vastness of time. As we continue drifting through this catalog of cosmic strangeness, we'll encounter planets that blur the lines between what is and what could be worlds that came close to being habitable but failed for reasons both subtle and profound. We'll explore the places where potential met reality and fell short, and ask ourselves what it means when a planet is almost right, almost perfect, but not quite. There are worlds out there that came so close to being like Earth planets that orbit in the habitable zone, that have the right size, the right distance from their star, the right conditions on paper, and yet something went wrong. Maybe the atmosphere is too thick, trapping heat until the surface became an oven. Maybe there's no magnetic field to protect against radiation. Maybe the star is too active, too violent, stripping away any chance of stability. These are the almost homes, the places that could have been sanctuaries for life, but became cautionary tales instead. And then there are the objects that couldn't decide what to be too massive to be planets, but too small to ignite, as stars stuck in between, glowing faintly in the dark, belonging to neither category fully. When we search for habitable planets, we start with a simple calculation. How much energy does a planet receive from its star? Too much and water boils away. Too little and everything freezes. The range where liquid water can exist on the surface is called the habitable zone, or sometimes the Goldilocks zone. Not too hot, not too cold, just right. But being in the habitable zone doesn't guarantee habitability. It's a necessary condition perhaps, but not sufficient. Earth is in the sun's habitable zone, but so is Venus, and Venus is hell. Kepler 452b was discovered in 2015 by NASA's Kepler Space Telescope, and the announcement generated significant excitement. This planet orbits a star remarkably similar to our Sun, a G-type main sequence star, only slightly larger and older. The planet itself is about 60% larger than Earth in diameter, making it a super-Earth, and it orbits within the habitable zone, completing one orbit every 385 days, just 20 days longer than Earth's year. The similarities were striking enough that some media outlets called it Earth's cousin or Earth 2.0. But the excitement was premature. Being in the habitable zone and being habitable are different things. Kepler 452b is larger than Earth, which means it likely has stronger gravity, perhaps 1.5 to 2 times Earth's surface gravity. If it's a rocky planet, which is uncertain, its composition might be different from Earth's, with a thicker atmosphere or more volcanic activity. We don't know if it has water. We don't know if it has a magnetic field. We don't even know for certain if it has a solid surface. It could be a mini Neptune, a small gas planet with no surface at all, just layers of atmosphere getting denser with depth. Research shows that planets in the super-Earth size range can go either way. Some are rocky, scaled-up versions of Earth. Others are gaseous, more like Neptune than Earth, despite being smaller. The transition seems to occur somewhere around 1.5 to 2 times Earth's radius, but there's no sharp boundary. Whether a planet ends up rocky or gaseous depends on how much gas it captured during formation and how much it's lost to atmospheric escape over time. The distance to Kepler 452b is about 1,400 light-years, far too distant for us to study in detail with current technology. We can't analyze its atmosphere. We can't measure its mass precisely. We can only observe the tiny dip in starlight when it transits its star and emphasize an orbital period from that. Everything else is educated guessing models and probabilities. It might be habitable. It might be a barren rock. It might not even be rocky. We simply don't know, and we won't know until we develop better telescopes or better methods. This is one of the frustrations of exoplanet science. We can detect thousands of planets, but detailed characterization is difficult. We know they exist, but we don't know what they're like. It's like knowing there are houses on a distant street, but not being able to see inside them, or even tell if they're made of wood or brick. The data are limited, and we have to be careful not to let our hopes fill in the gaps. Kepler 22b, discovered in 2011, faces similar ambiguity. It's about 2.4 times Earth's radius, orbiting a star slightly smaller and cooler than the Sun, completing one orbit every 290 days. It sits comfortably in the habitable zone, receiving about 25% less energy from its star than Earth receives from the Sun, comparable to the energy Earth would receive if it orbited at Mars's distance. Models suggest the surface temperature could be around 22 degrees Celsius if the planet has an Earth-like atmosphere and greenhouse effect. But again, we don't know if it's rocky. At 2.4 Earth radii, it's more likely to be a mini Neptune than a rocky super-Earth. If it has a thick hydrogen and helium atmosphere, the surface pressure could be crushing thousands of times Earth's atmospheric pressure, making it utterly inhospitable despite being in the right temperature range. Or maybe it's a water world with a global ocean hundreds of kilometers deep and no solid surface. Or maybe it's rocky with a thin atmosphere and liquid water on the surface, a true Earth analog. The data don't tell us. We're left guessing. One of the lessons here is about the danger of wishful thinking. When we find a planet in the habitable zone, especially one orbiting a sun-like star, we want it to be habitable. We want there to be another Earth out there, a place where life could exist, where perhaps it already does. But the universe doesn't care what we want. Most planets, even those in the habitable zone, are probably not habitable. The conditions for life are specific, delicate, easily disrupted. Earth is the exception, not the rule. Scientists have identified several factors that contribute to habitability beyond just being in the habitable zone. A planet needs a stable climate, which requires a stable star. Our sun's luminosity varies by less than 0.1% over its 11-year solar cycle. Some stars are much more variable, experiencing flares and eruptions that could sterilize nearby planets. A planet also needs protection from radiation, which on Earth comes from our magnetic field generated by the churning molten iron in our core. Without a magnetic field, stellar wind and cosmic rays can strip away the atmosphere over time. A planet needs plate tectonics to recycle carbon and regulate atmospheric carbon dioxide levels, maintaining a stable greenhouse effect. Earth's continents drift, collide, subduct, and create new crust in a continuous cycle that's been operating for billions of years. We don't know if other rocky planets have plate tectonics. Venus doesn't, Mars doesn't. It might be rare, a consequence of Earth's particular size composition and thermal evolution. A planet also needs a large moon to stabilize its axial tilt, preventing chaotic variations in climate. Earth's moon, formed by a giant impact early in our planet's history, keeps Earth's tilt stable at about 23 degrees, giving us regular seasons and preventing extreme climate swings. Without the moon, Earth's tilt could vary wildly, making the climate unpredictable and possibly hostile to complex life. When you list all these requirements, habitability starts to seem improbable. Yet, here we are, existing on a planet that meets all these criteria. So, it's possible. The question is how common it is. Are habitable planets abundant waiting to be found with better instruments? Or are they extraordinarily rare flukes of cosmic chance scattered sparsely across the galaxy? Now let's turn to the objects that blur the line between planet and star. Brown dwarfs are sometimes called failed stars, objects that formed like stars from collapsing gas clouds, but didn't accumulate enough mass to ignite hydrogen fusion in their cores. The minimum mass required for sustained hydrogen fusion is about 75 to 80 Jupiter masses, depending on composition. Below that threshold, the core never gets hot enough for fusion to start. The object contracts, heats up from gravitational compression, glows faintly in infrared, but never becomes a true star. Brown dwarfs occupy the mass range between about 13 Jupiter masses, the minimum mass required for deuterium fusion, and about 80 Jupiter masses, the threshold for hydrogen fusion. They're more massive than planets, but less massive than stars, a distinct class of object with properties intermediate between the two. They have atmospheres with clouds and weather. They emit heat from their interiors. Some have magnetic fields, but they don't shine like stars because they don't have a long-term energy source from fusion. The first brown dwarf was confirmed in 1995, an object called Gliese 229b, orbiting a red dwarf star. Since then, hundreds have been discovered drifting alone in space or orbiting other stars. Their surface temperatures range from about 500 to 2,000 degrees Celsius. For the coolest ones, comparable to a hot oven, up to several thousand degrees, for the youngest and most massive. Over time, brown dwarfs cool and dim, radiating away their internal heat until they become cold, dark objects barely distinguishable from large planets. The distinction between a very massive planet and a low-mass brown dwarf is murky. If both have the same mass, say 15 Jupiter masses, what determines which category they belong to? Scientists suggest the differences in formation, mechanism. Planets form from the bottom up, starting with a solid core that then captures gas. Brown dwarfs form from the top down, collapsing directly from gas clouds like stars. But this distinction is hard to confirm observationally. If you discover an isolated object drifting through space with a mass in the overlap range, you can't tell how it formed just by looking at it. Some objects challenge classification entirely. SIMP J 0, 1, 3, 6, 5, 6, 6, 3, plus 0, 9, 3, 3, 4, 7, 3, often shortened to SIMP 0, 1, 3, 6, is a free-floating object with a mass about 12.7 Jupiter masses right at the boundary between planet and brown dwarf. It's young, about 200 million years old, and has a strong magnetic field that produces radio emissions detectable from Earth. It was initially classified as a brown dwarf, but its mass is so close to the planetary range that some scientists consider it a rogue planet instead. The designation matters for statistical studies for understanding formation processes, but the object itself doesn't care what we call it. Brown dwarfs were once thought to be rare, but surveys have found that they're actually quite common, perhaps as common as stars in some regions of the galaxy. This has implications for planet formation. If brown dwarfs form the same way stars do, just with less mass, then the process of forming stars and the process of forming giant planets might overlap more than we thought. Maybe there's a continuum with no clear boundary, just a gradual transition from planets to brown dwarfs to stars as mass increases. One fascinating aspect of brown dwarfs is that some have planets orbiting them. These planets orbit objects that aren't quite stars in systems that might be more common than we realized. The habitability of such planets is questionable. Brown dwarfs cool over time, so even if a planet starts in a warm zone, it won't stay warm. A planet orbiting a brown dwarf would experience a slowly dimming sky as its host cools and fades. Eventually, the brown dwarf would become too cool to provide significant heat, and the planet would freeze unless it had substantial internal heating. There's also the question of what a sky would look like from a planet orbiting a brown dwarf. The brown dwarf would appear much larger than the Sun appears from Earth, because the planet would have to orbit very close to receive any significant warmth, and the light would be deep red or infrared outside the range of human vision. Plants, if they existed, couldn't photosynthesize with visible light because there wouldn't be any. They'd have to adapt to infrared if that's even possible. Life, if it emerged, would be fundamentally different from anything on Earth. One common misconception is that brown dwarfs are just large planets. They're not. They're distinct objects with different formation histories and internal structures. Even the most massive planets are structured around solid or liquid cores with gas envelopes. Brown dwarfs are fully convective with heat transported from the interior to the surface by churning gas more like a giant atmosphere with no surface beneath. The physics is different. The evolution is different. The classification is different. Another misconception is that failed star implies something defective or inferior. But brown dwarfs aren't failures in any meaningful sense. They're successful brown dwarfs, objects that formed and exist according to the laws of physics. They just don't fuse hydrogen. That's a category distinction, not a value judgment. The universe doesn't grade its creations. When we think about the almost homes and the failed stars, we're really thinking about how close things can come to being something else and yet remain fundamentally different. Kepler 452b is so close to being Earth-like, but close doesn't count in planetary science. Brown dwarfs are so close to being stars, but they never quite make it. The boundaries are sharp even when the differences seem small. A planet 1% smaller or larger might be habitable or inhospitable. A brown dwarf 1% more massive might ignite fusion and become a star. Small changes lead to fundamentally different outcomes. As we near the end of this journey through cosmic strangeness, we've seen planets that defy expectations, that challenge our definitions, that remind us how little we truly understand about the diversity of worlds. We've drifted through glass storms and diamond cores, through eternal twilights and absolute darkness, through water, deeper than continents, and lava flowing like rivers. We've met the oldest and the youngest, the lightest and the heaviest, the almost perfect and the utterly alien. And now, as the night deepens and our drift slows, it's time to gather these threads together, to rest in the wonder of it all, and to let the strangeness settle into something like peace. We've traveled far tonight, you and I, through worlds that rain glass and diamonds, through planets locked in eternal twilight, through the cold darkness of rogues wandering alone. We've stood on oceans deeper than imagination and watched lava flow like water under alien skies. We've met planets older than most stars and others still being born from cosmic dust. We've seen the almost homes that came so close to being sanctuaries and the failed stars that couldn't quite ignite. And through it all, one truth keeps returning: the universe is stranger than we ever allowed ourselves to believe. When the first exoplanet orbiting a sun-like star was confirmed in 1995, 51 Pegasi, B astronomers thought it might be an outlier, an unusual case that would help us understand the norm. But 30 years and 5,000 planets later, we've learned something humbling. There is no norm. Every planetary system is unique, shaped by its particular history of formation, migration, collision, and chance. The patterns we see in our solar system, rocky planets close to the sun, gas giants farther out, orderly orbits, stable configurations. Those patterns are not universal laws, but local accidents. Think about what that means for a moment. Everything we thought we knew about how planets should be was based on 8 examples, 9 if you count Pluto, all orbiting the same star, all formed from the same protoplanetary disk. We built our models on that tiny sample size and assumed they would apply everywhere. But the universe had other plans. It created hot Jupiters orbiting closer to their stars than Mercury orbits the Sun. It created super-Earths, a category that doesn't exist in our solar system at all. It created planets orbiting binary stars, planets orbiting dead stars, planets with no stars, planets made of materials we only barely understand. Scientists now estimate that nearly every star in the Milky Way has at least one planet. With roughly 200 billion stars in our galaxy, that means hundreds of billions of planets, possibly trillions, when you include rogue planets drifting through interstellar space. The sheer number is overwhelming. We've discovered 5,000. We've characterized perhaps a few hundred in any detail. The vast majority remain unknown, invisible, waiting in the dark for telescopes and techniques that haven't been invented yet. And each one of those planets has a story, a formation history stretching back billions of years, a present state of geology, atmosphere, temperature, composition, a future of cooling evolving, possibly being consumed when its star expands into a red giant, or ejected when its system becomes unstable. Planets are not static objects, but processes ongoing experiments in what matter does, when gravity gathers it together and time works on it. Research shows that planetary diversity is even greater than we can currently observe. Our detection methods are biased towards certain types of planets. The transit method favors large planets orbiting close to their stars, because those produce the biggest, most detectable dips in starlight. The radial velocity method also favors massive close-in planets because they cause larger wobbles in their stars. Small planets in distant orbits are much harder to detect with current technology. This means the catalog of known exoplanets is skewed toward extremes. The strange planets might actually be common, while the Earth-like planets we hope to find remain mostly hidden. The James Webb Space Telescope, launched in 2021, is beginning to change that. Its infrared capabilities allow it to analyze exoplanet atmospheres in unprecedented detail, detecting molecules like water vapor, carbon dioxide, methane, and sulfur dioxide. In 2023, JWST observed WASP-96b and detected clear evidence of water and clouds in its atmosphere, demonstrating the telescope's ability to characterize worlds light years away. This is just the beginning. Over the coming years, JWST will observe dozens of exoplanets, building a chemical census of alien atmospheres, searching for biosignatures, molecules that might indicate the presence of life. But even with better telescopes, some questions will remain unanswered for a long time. We can detect planets. We can measure their size, mass, orbital period, and sometimes atmospheric composition. But we can't yet see their surfaces. We can't watch their weather in real time. We can't map their continents or photograph their moons. The distances are too vast, the planets too small and dim. It's like trying to study a grain of sand on a beach 50 miles away while standing next to a bonfire. The glare from the star overwhelms the faint light from the planet. Scientists are developing techniques to overcome this limitation. Starshade's large spacecraft that would fly in formation with telescopes and block starlight, allowing planets to be seen directly. Coronagraphs, instruments that create artificial eclipses inside telescopes. Interferometry, combining light from multiple telescopes to create effective apertures hundreds of meters across. These technologies are being tested, refined, proposed for future missions. Maybe in 20 years, maybe in 50, we'll have images of exoplanet surfaces, actual photographs of alien worlds, showing clouds, oceans, continents, storms. Until then, we work with indirect measurements and models, piecing together pictures from fragments of data. One of the questions we haven't answered yet is whether any of these strange planets harbor life. Life on Earth exists in an extraordinary range of environments, from boiling acidic springs to frozen Antarctic ice, from crushing deep-sea pressures to the near vacuum of high altitude. If life can adapt to those extremes here, maybe it can adapt to the extremes on other worlds. Maybe glass rain in tidally locked hemispheres and subsurface oceans heated by internal radioactivity aren't barriers to life, but just different sets of challenges that evolution could solve given enough time. Or maybe life requires conditions so specific that Earth is the only place it's ever emerged in the entire observable universe. We don't know. We have one example, one biosphere, one genesis of life. Everything else is speculation until we find a second example. And maybe we will. Maybe one of the thousands of exoplanets we've discovered hosts microbes in its oceans or complex organisms adapted to its unique environment. Maybe we'll detect biosignatures in an atmosphere, oxygen and methane in disequilibrium, a chemical signature that can't be explained by geology alone. Maybe we'll receive a signal, an unmistakable pattern in radio waves that could only come from intelligence. Or maybe we're alone. Maybe despite the billions of planets, despite the diversity and strangeness, life is so improbable that it's only happened once. The question remains open, and it might remain open for generations, perhaps for centuries. But the search continues. Every new planet discovered is another chance, another possibility, another place where the universe might have created something living. Have you ever wondered what future humans will think when they look back at this moment in history? We're the first generation to know that planets are common, that our solar system is not unique, that the stars are surrounded by worlds. For most of human history, planets meant the wandering lights visible to the naked eye: Mercury, Venus, Mars, Jupiter, Saturn. Then we discovered Uranus and Neptune. Then we confirmed exoplanets existed. Now we catalog them by the thousands. In just 30 years, our understanding has exploded from theory to certainty to census. And we've learned something about ourselves in the process. We've learned that Earth is not the center of anything, not the center of the solar system, not the center of the galaxy, not the center of the universe. We're on a medium-sized rocky planet, orbiting a medium-sized yellow star in the outer regions of a medium-sized spiral galaxy. There's nothing special about our location, nothing unique about our star, nothing that marks us as central or important to the cosmos. We're one world among billions, fortunate to be habitable, fortunate to have given rise to life, fortunate to have evolved intelligence capable of asking these questions. It's a humbling perspective, but it's also liberating. If we're not the center, then the universe is bigger and stranger than we are. There are things out there we don't understand, phenomena. We can't explain, worlds that defy our categories. And that's wonderful. That means there's always more to discover, always another mystery waiting beyond the current edge of knowledge. The strangeness we've encountered tonight is just a sample, a small taste of the cosmic diversity that exists across billions of light years and billions of years of time. The weirdest planets we've found, the glass rain worlds, the tidally locked twilight zones, the rogue wanderers, the water worlds and lava oceans, the puffballs and super dense cores, the ancient relics and newborn giants, the almost homes and failed stars. They're all real. They're all out there right now, orbiting, rotating, evolving, existing in states we can barely imagine. They don't need us to observe them. They don't need us to understand them. They simply are following the laws of physics wherever those laws lead, creating patterns and structures and stories written in gravity and heat and time. And maybe that's the deepest lesson. The universe doesn't exist for us. It doesn't care about our hopes or our definitions or our assumptions. It just creates endlessly and without purpose every possible variation allowed by the fundamental forces. We happen to be here to witness a tiny fraction of that creation, to catalog and study and marvel at it. We're tourists in a cosmos that was here long before us and will be here long after we're gone. The planets will keep orbiting the stars, will keep burning the galaxies, will keep expanding into the dark, whether we're watching or not. But while we're here, while we have consciousness and curiosity and the ability to wonder, we can look up at the night sky and know that among those points of light are worlds beyond counting. Some are familiar, rocky, and temperate. Some are strange beyond description. All are real. All are part of the same universe we inhabit, governed by the same physics, made of the same fundamental particles, connected to us by the vast web of gravity and light that binds everything together. Tonight, we've drifted through that strangeness together. We've let curiosity guide us through worlds that challenge understanding. We've seen beauty in the deadly and pattern in the chaos. We've remembered that the cosmos is larger than ourselves, stranger than we imagined, and full of wonders we're only beginning to discover. And now, as our journey together comes to its end, as the night deepens and the stars breathe their slow light across the dark, it's time to rest. Thank you for staying with me through this long, quiet drift across the galaxy. Thank you for your curiosity, your patience, your willingness to wonder. The universe is vast, and we've only touched a small corner of its strangeness tonight. But there are more stories waiting, more mysteries to explore, more quiet nights, where we can drift together through the cosmic dark and let wonder do the work. If you enjoyed this journey, there will be others, more stories told softly in the dark, more science whispered like secrets, more chances to remember that we're small and the universe is large, and that's exactly as it should be. Until we meet again under different stars with different questions, keep looking up. Keep wondering, keep drifting, sleep well, dream of distant worlds. And remember, somewhere out there glass is raining sideways through hurricane winds, and iron is falling from metal clouds, and ancient planets are circling dead stars. And somewhere, maybe something is looking back at us across the light years, wondering if we're strange too. Good night.